Hello, can you hear me?
Good morning, Prof. Yes, we can hear you.
Yeah. So today we are going to continue chapter 2C, which is the continuation from chapter 2B. So we will emphasize on the input signal, which is PRBS theory, analysis, and applications. Okay. So as I told you before, PRBS stands for pseudo random binary sequence. Okay, so this is a special signals, which is periodic but random inside. Okay, with binary sequences. This is examples of PRBS generators, 16-bit switch hardware, which being used in industry and in the research field. Okay. So pseudo-random binary sequence, or PRBS, is probably the most convenient inputs for linear system ID. Okay, so the ACF of PRBS provides ACF. ACF is the autocorrelation functions of PRBS, provide the best and useful approximations to periodic white noise. Okay. So it is also a forcing functions, mostly widely used in statistical system testing. So this one also described in the book chapter that I attached yesterday or yesterday's 2 days ago. A book chapter. Have you received it in WhatsApp?
Yes, Prof.
The general form is shown in the figure below. Okay, so it's a special case of the random binary functions. So if you look here, usually it have a plus minus 1 volt, but every time it goes to minus 1 volt is 0, 0, 1, 0, 0, 1, 1, 0, 0, sorry, 1, 1, 0, 0, 1, 0, 1, 0. Okay, so that is the PRBS general form. But after one periodic, after one period, it will repeat again. Okay, it will repeat again. Similarly to the ACF, the autocorrelation functions, it will repeat again. Okay, so this is a 15-bit PRBS. Okay. Why 15 bits? Because after 15 bit, it will repeat again. Okay, at the signals and at the autocorrelation functions. 15-bit pseudo-random binary sequence and its autocorrelations. So the nature of PRBS is it can take only two possible states. Okay, either positive A or negative A, or positive 1 or negative 1 volt. Okay, or positive 5 and negative 5 volt. PRBS state can change only at discrete intervals, which is known as the sampling time delta t. So the change occurs in the deterministic pseudo-random manner, and PRBS is periodic with a period of t equal to n delta t. So delta t is the sampling time, and capital N is an integer. So PRBS, as known, is a repeatable signal satisfies the conditions of randomness. There are about three conditions of randomness. First is the balance property. Okay, so balance property said that in any period of the sequence, the number of logic ones should not differ from the number of logic zero by more than one. Okay, so this is the, we call it as a balance property. Okay, or we call it as a logic 1 or logic 0 lah. Second properties is the run property. So among the runs of 1, 2, 3, etc. in the period half should be of length 1, a quarter of length 2, and 8 of length 3, and etc. And there are many of the each one logic 1 as logic 0 state. Okay, so we will go through this when we design the PRBS generator. And then finally, the correlation property is about same like balance property. If a period of the sequence is compared term by term with any cyclic shift or itself, the number of agreements and disagreements, agreement usually 1, disagreement usually 0, should not differ by more than 1. So from the book, the type of PRBS, we have two types. One is QRC, quadratic residue code, and the second one is MLS, maximum length sequence. So the most commonly used is for PRBS is the maximum length sequences. So the integer, the n, the capital N that I mentioned integer in the previous slide is defined by capital N is equal to 2 power of n minus 1, where small n is an integer, where n is equal to 15, 31, 63, 127, and 255. Okay, so this can be generated by n stage shift register. So n is the maximum, is the integer. Okay, it is equal to 2 power of small n minus 1. Small n is known as a stage shift register, with the first stage determined by feedback of the appropriate modulo to sum, okay, of the last stage and 1 or 2 earlier stage. Okay, refer to figure 7.14. So now you have shift register 1, shift register 2, shift register 3, shift register 4, shift register 5, and shift register 6. 1, 2, 3, 4, 5, 6. Okay. And we take 5 and 6 as a modulo to additions, okay, which is known as XOR function in digital logic. Okay. And then the output will be fed back to the shift register 1. So the logic will be moved from SR1 to 2, 3, 4, and 5. Okay, with triggered by the clock pulse. Okay, every delta t seconds. So modular to additions is the logic function exclusive OR. Okay, meaning that if the inputs are the same, the output is logic 0. If the input are different, the output is logic 1. Okay, so 0, 0, 0, 1, 1, 0, 1, 1. So if we apply XOR, 0, 0 is 0, 1, 1 is 0, and different 1, 1. So this is the function of XOR or modulo to sum. So remember this one, okay? So alternatively, it can be thought as a binary additions where only the least significant digit is recorded. So the logic content of the shift register are moved one stage to the right every delta t seconds, but simultaneously triggering by a clock pulse. So all possible states of the shift register are passed through except that of all zeros. The output can be taken anywhere from any stage. So you can take anywhere, you can take it from here as the output of 4 or here as output, no problem, anyway. Okay. As long as it's in the period of n delta t, if the feedback is taken from the modulo to sum, of the wrong register stage, then the resulting cyclic will not achieve maximum length sequence, and it is not a PRBS, right? So the correct stage for the feedback configurations is here. If you are using a two shift register, okay, so the maximum length sequence is n. Okay, so n is equal to 2 power of 2 minus 1, so it's equal to 3. Okay, the MLS. So the feedback that you should use is 1 XOR 2. If n is equal to 3, okay, so this one n will be 2 power of 3 minus 1, which is 7. Say maximum length sequence 7, so you should use 1 XOR 3. Okay, and go for the N15, 31, 63, 127, 255, 511. The maximum length sequence, okay, until 1023. But if you want to use a longer PRBS, so you should use this one, which is stated in the journals. Okay, this one. Okay, it's very long. Okay, this one is provided in the textbook. Okay, from the book chapter that I attached previously. So the second type of PRBS is known as quadratic residue codes, QRC, where the maximum length sequence is n equal to 4k minus 1, where k is an integer and n is a prime number. Okay, so it is 11, 19, 23, 31, 43, and 47 is a prime number, the number that can divide by 1 and itself. Okay, other number cannot be divided. So this one is difficult to generate due to the fact that using logic secretary, but the sequence can be pre-computed and read from the paper tape or slower applications. QRC advantage is that successive sequence lengths are much close together. Okay, so we focus on MLS, maximum length sequence, in this chapter. Okay, which using a difference equations here. Okay, where dm denotes the delay operator and positive circle is the modulo to sum or XOR functions, which is this one. Okay, same input, logic 0, different input, logic 1. In order to generate the maximum length sequence, okay, the characteristic equation must be primitive and irreducible. For example, if you want to generate MLS equal to 7, okay, for example, example 1. Design maximum length sequence equal to 7. Okay, so in order to do that, we have use this one, n is equal to 2 power of n minus 1. Okay, where n is equal to 3. Okay, which is a number of shift register. Okay, so that's why n is equal to 2 power of 3 minus 1 is equal to 7, the MLS. So we design the the shift register. Okay, SR1, SR2, SR3, and each shift register will give a clock pulse. Okay, right? And then for maximum length sequence 7, so we have to refer to the table just now, this one. 7, okay, so 3 shift register, maximum length sequence 7, and you must use feedback configuration 1 XOR 3. 1 XOR 3, which is this is 1 XOR 3, okay, and the output of the feedback goes to the shift register 1, okay, and the output is here, okay. Okay, guys, understand? Right. So in order to do that, we have to construct a table for simulations. Okay. Okay. Okay, guys. And then we clock pulse we set to 111 first initials. Okay. Okay. So now when we goes to the 1 XOR 3, this one XOR 1 1. So same input, the logic 0. Okay, and then this 0 will go here. This one will shift to the right. Okay. Then 0 XOR 1 is 1. This one will go here. 0 will shift to the right. 0 1. Okay. And 1 1 XOR, you will give 0. So 0 1 0. 0 0 will give same input. So same input is 0 0 0 1. 0 1 different is 1. So 1 0 0. 1 XOR 0 is 1. So 1 1 0. And 1 XOR 0 is 1 1 1 1 again. Okay. So you can see that after this is 1 2. After length 7, so it will repeat back again. See, you repeat back again. Can you see that one? After 7 bit, the PRBS signal will repeat again. That's why when we plot the clock pulse, okay. So the logic we take from here, the output is here. This is the output. Because we stated here the output here, okay, shift register 3, so it is 1 1 1 0 1 0 0. Okay, okay. So the plot will be 1 1 1 for 1 clock pulse. Then goes to 0 0, 1, 0, 0, 0, 1, 0, 0, and then goes to 1 back again. Okay, so this is 1, 1, 1, 0, 1, 0, 0, then 1. So this is one period. Okay, T is equal to n delta T. Okay, where n is equal to 7. This is your clock pulse, and this is your PRBS. Okay, shift register 3. If you want to take from shift register 1 also can, shift register 2 also can. Okay, as I mentioned here, okay, so exactly the same. Okay, so this is the modulo to sum. Okay, U. Okay, this is the shifted. We started with 1, 1, 1, 1. Okay, and then after 7 bit, it will repeat again 1, 1, 1, 1. So you can take the output from here, also can, or from here also, and from here also can. So I took from here shift register 3. So we get a 1, 1, 1, 0, 1, 0, 0, which is shown here. Okay. So you can plot the from here as well, also can shift register 2 or shift register 1. It's the same thing as well. So from the table, state 8 is equal to state 1, which is length 7. Then the sequence repeat. Okay. So usually converts the 0 to be -1, 0, which is a -1 volt. We convert to 0, which is a PRBS form. Example 2. So design a PRBS generator to produce a maximum length sequence which is equal to 15. Okay. So again, design which is a maximum length sequence equal to 50. Okay. So n is equal to 2 power of n minus 1, which is equal to 15. So what is the n value? N is equal to?
N equal 4.
So that's why n is equal to 2 power of 4 minus 1. So we will get 15, the length of the maximum length sequence. So how many shift register? So we have a 4 shift register. Okay, 1, 2, 3, 4. Okay, so each will be given a clock pulse. Okay. Then the feedback configurations. Feedback configurations, we follow the table. Which is here. Okay. 3XO4. So actually, for 15, we have 2 feedback configurations. This one. 3XO4 or 1XO4. Okay. So both can be, both are true. 1XO4. Okay, 1XO4. 3XO4. Go to the input. Okay. And then this is the output. Okay, so CP is the clock pulse, right? Or you can do like this. Okay. Clock pulse. 1 XOR 4 also can. Okay. Okay, guys, so we simulate this one first. Okay. XOR 4. Okay. So we start with 1 first. Okay. So this is number 1, 2, 4, 5. Okay. So 1 XOR 1, 0. Okay. 0, 1, 1, 1. 1 XOR 1, 0, 0, 0, 1, 1. 1 XOR 1 is 0, 0, 0, 0, 1. 0, 1, 1, 1, 0, 0, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0, 0, 0, 1, 0, 1, 1, 0, 0, 1, 1, 1, 0, 0, 0, 0, 0, 0, 1, 1, 0, 1, 0, 1, 1, 0, 1, 1, 1, 0, 0, 1, 0, 1, 0, 1, 1, 1, 0, 1, 0, 1, 0, 1, 1, 1, 0, 1, 1, 0, 1, 1, 1, 1, 0, and 1, 0, 1, and finally you will get that the at the 16th, okay, at the 16th it will repeat again 1, 1, 1, 1, which is same as step number 1. Okay, this one is 16. So we'll repeat again. Okay, so you can simulate this one as well. Okay, simulate this one again, and then you will get the same repeat after 15 bits. Okay, try 1 XOR 4. Okay. So in this case, 3 XOR 4. Okay, you XOR it, and then you get the maximum length sequence is 15. Start with logic 1. Okay, using a 4 shift register. Okay, with configuration 3 XOR 4. The output goes to the shift register 1 and can be tapped from any SR, either 1, 2, 3, or 4. Okay. So Consider illustration of the above. A 4-stage register with feedback 3 XOR 4 is okay, but successive states of the shift register starting all ones are shown here. Okay, sini sama aja cerita dia. Okay, same story. Okay, this is number 1, 2, 3, 4, 5, 6, 7, 8, 8, 9, 10, 11, 12, 14. See that after 15, at state number 16, it will repeat again as number 1. So this one is considered as one cycle, one period. Okay. After 15, at the state 16, the patterns will repeat again. Verify your answer in example 2 using a 4-shift register with 1 XOR 4. Okay, and the output goes to SR1. What is your observations? Yes, it is the same maximum length sequence, i.e. 15. Okay, so 2 options of feedback for n is equal to 15. Okay, so consider illustration of the above 4-stage register with feedback from 1 and 4. Okay, so dia akan repeat juga, sama juga lah. Okay, 1 and 16. Okay, repeat again. But based on your answer in example 2 and 3, okay, we are using a 4-shift register with a feedback configuration 2 XOR 4. What happened? What is your observations? MLS not achieved. Okay, due to wrong feedback configurations. Okay, so maximum length sequence 15 is not achieved. Okay, shown here. Okay, because of the wrong XOR. So this is 1, 2, 3, 4, 5, 6, 7. So you can see that at 7 it will repeat again. Supposed to be 15, but at 7 it already repeats. So it is not a maximum length sequence. Not maximum length sequence. So by looking at the properties of randomness, when we apply a 15-bit sequence, okay, number of 1 is 8, number of zeros is 7, so the difference is 1. Okay, so that is for the balance property, it fulfilled. For the run property, we have a length of run of 1, 2, 3, and 4. And this is the number of runs, which is 4, 2, 1, 1. And the actual ratio is 4 divided by 8, 2 divided by 8, 1 divided by 8, and 1 divided by 8 by a total of 8. And the other ratio is half, quarter, 1/8, and 1/16. And it fulfills the run property. And the correlation property also have a number of agreements of 7, number of disagreements of 8, and the difference is 1, which fulfill the property of randomness. So if the output of the stage 1 and stage 2 to 4 give a delay of 1 to 3, 4 XOR 1 give a delay of 4, 4 XOR 1 and XOR 3 give a delay of 11. So this is how we calculate the delay for the PRVS. So this is a sample of assignments, okay, PRVS of 63-bit design. 63-bit design meaning that n is equal to 63. So n is equal to 2 power of n minus 1. So what is the value of n in order to produce 63? n equal to 6. 2 power of 6 minus 1. So you get 63. So this is the design. Okay. So it also have two options. Okay. Option number 1 is 5 XOR 6. Option number 2 is 1 XOR 6. Okay. So by using MATLAB, okay, we can design the flip-flop. Okay. Design the flip-flop, and then as shown here. Okay, so the scope is to monitor the signals, and this is the clock path. Okay, connected to the each of the flip-flop, the CLK. Okay, and this is the XOR functions. So we can put it in the hardware, okay, using Proteus to simulate the circuit designs. Okay, as shown here. Okay, so it's a sample of assignments and amplitude varying circuit to increase the amplitude of PRBS. For example, we get this one, 1 volt. So you can increase it to 5 volt. Okay, the amplitude, okay, by using this amplitude varying circuit diagram. And you simulate, okay, SR5 XOR XR6. So it will repeat at 1, 1, 1, 1 after 63. Okay. And 1 XOR 6, 1, 1, 1, 1, 1. And at 60, after 63, you will repeat again at stage of 64. And this is the PRBS 63-bit design, okay, hardware design. It's very compact and very portable, okay, as shown here. So you can see that the LED red and green, okay. So when the LED is red, lighting, so meaning there is a logic 1. If not lighting, is logic 0. Okay, so it uses power supply of DC 9 volt and a potentiometer to varying the amplitude of the PRBS. You also can simulate using a 63-bit simulating the PRBS 63-bit. So this is the 63-bit maximum length sequence of PRBS that will be injected to the unknown model system. Okay. Okay, guys, we stop here at slide number 38. So I'm in KL now. After the class, I will move back to JB. Okay, after 1 week holiday, visiting my second grandchild. Is there any questions? Next week is the test 1. Any question, guys?
Prof, for the frequency response, we cannot in the exam.
Yeah. Until frequency response identification, the introduction, impulse and time response identifications, and frequency response identification. Until that, correlation not included. Chapter 2B not included until chapter 2A. Okay?
Okay.
Okay. So see you guys next week. Okay? Bye.